Good afternoon and welcome to today's webinar from Timber Development UK in association with Rothoblaas. In a minute, we're going to be hearing from Andrés Reyes García from Rothoblaas, all about understanding premature failings in timber steel fixings. But just before we get started, I'm going to just say a few little words introducing Timber Development UK. TDUK was formed in 2021 from the merger of the Timber Trade Federation and TRADA. This has created the biggest supply chain body in the UK for the timber sector. We include everybody from architects and engineers to sawmills, importers, merchants, joiners, everyone involved in timber, essentially. You can see there are three missions: to connect the supply chain, lead best practice, and accelerate a low carbon future. And we do this via webinars like this one, but also lots of other outputs. There you can see one of our two flagship magazines, that's Designing Timber. It also has a sister magazine, Supplying Timber, and between them they cover all the essential timber news, whichever part of the industry you're in. You can read stories of inspiring timber buildings, pick up CPD, read about the latest building regulations and general guidance, anything and everything along those lines. You can also see there on screen another of our publications about moisture management. We recommend that anybody in the world of timber design downloads that document and has a browse of all the other great material you can find in our knowledge library. Speaking of which, there's an example of one of our timber knowledge sheets using SIPs. Our knowledge sheets cover that kind of technical information, regulatory information, sustainability information, design guidance, you name it. You'll be able to find a timber knowledge sheet on that topic. And next to it, you can see one of our many case studies. We have hundreds of case studies in our library. That one is for Cotto House, really interesting building. We did a webinar on that, and actually along with this webinar, you can find plenty of other webinars on the TDUK YouTube channel. There's an example of one of our recent issues of Designing Timber with Rafter Walk, a really interesting infrastructure project in London's Canada Water there. Good use of tropical hardwoods, among other things. So while many of our resources that I've just shown you are free for anybody who registers with us, there are some resources that are member only. And we'd really like you to join us if you're not a member. It supports fantastic webinars like this one. It supports our conferences. Every year we have the UK Timber Design Conference. Every summer we have the Global Markets Conference. We do an awful lot of lobbying work. We're really fighting your corner if you're in timber. So please do consider joining us. Just a bit of housekeeping. You might notice there's a Q&A box at the bottom of the screen. Please do ask any questions, just type them in there. We'll make sure there's plenty of time for asking questions at the end, but you can also type your questions as we go along. And actually, even if you don't have a question but want to share something about the topic, if you want to share any perhaps tips you have on ensuring the integrity of structural elements when you're in a timber steel project, things that you've found, anything you'd like to share, any other resources. So yeah, feel free to put them in the Q&A box. I'm now going to hand over to Andrés, and we'll start today's webinar proper. Thank you. Over to you, Andrés.
Thank you. So I'm sharing here. Do you see my screen now?
Just give it a second. I can, yes.
Perfect. Okay.
Even better. Thank you.
Thank you. So I'm Andrés Reyes García. I'm a civil engineer and I work for Rothoblaas since eight years. I'm product line manager for screws and concrete anchors. So I mostly deal with research and development for the screws and concrete. I am also an expert for SEN the European Commission, the technical committee and the working group for fasteners. So I also deal with normation and with standardization. And I'm going to share with you some of our, let's say, what we know so far about premature failures in timber steel fixing. Actually, it would be more correct to say timber to metal fixings in general. So yeah, let's go. So this is what we're going to talk about. This is the main topic, and I like this picture because it shows everything that needs to add up for failure to happen. Even, I mean, maybe combine of everything, the combination of everything, but also the single things that can happen that can lead to failure. In this case, where we can find failures happening is mostly when these conditions are combined, and you see here a thick metal plate in a wood connection, in connection with wood. Will you see some water, some moisture there, some corrosion, and some screw or some misinstallation, some let's say features of installation, improper installation. And these are generally there. We'll see it in the presentation, what happens and how these factors can then lead to a premature failure in timber buildings. We're not talking here about something that happens every time. Our very rough estimation is that a failure happens like one each 1,000 projects, more or less. Most of them are harmless, but it can happen that they can lead to a bunch of problems. They can lead to problems. So we're going to talk about why they happen, and we're going to give some guide into how to handle the situations. So why is this relevant now? This used to be the wooden building, like the most common, the typical wooden building. This is, I would say, the last from 10 years ago, maybe 15, maybe 20 more. So every time time passes by, this is not anymore the regular building we're seeing today. It looks more like this. So like multi-story building. We're talking about bigger elements, structural elements, connections, or let's say hybrid or mixed buildings with other materials like steel or concrete. And this is what has become the regular, the common for the common case for timber building now. And we're going bigger and bigger. So this is also becoming a standard. So bigger buildings, more stories, and meaning more complex connections. Also, we are hitting the 100 meters. We have already overpassed it, but this is becoming more and more the common ground for timber buildings. That means also that for connections passed from being started being this is what general connection was until, I don't know, maybe 10 to 15 years ago, to this is what connections looks like today in this type of building. So we need these connections, of course. We need plates and connectors to be robust, to be bigger, to support everyday bigger buildings. And that's also why we need carbon steel screws. We need high strength screws. So we need to keep improving these connections and also some let's say more fascinating buildings, some more complex architecture requires more complex connections as well. As the one that you can see here, see the amount of connectors and screws and the thickness of the plate. And that also means that the construction sites, the job site, passed from started lasting weeks to lasting months, and that makes a huge difference, because in this period we will have, of course, water, we will have moisture, and this is what a job site with moisture looks like. So we have probably We can have water stagnation, then decay of the wood. And well, this is also a case that is, we would like it to be rare, but it's actually, if you work in the timber sector, this type of thing happens also. And this is a multi-story building, so you see they already closed the envelope, let's say the windows, and the timber is not yet wet, it's not yet dry. So of course this has an impact. And the picture of the left, you see it has an impact on the performance of the wood, as we know. But connections tend to be generally are also the place where water drains. So you see that this has an important impact on the connections. The designer of this connection is very likely designed a service class 1 connection. But I don't know if you can say that this connection is right here in a service class 1. Also for other types of connection, that was beam to column joint, but also linear connections in the horizontal panels can be affected from water stagnation. But what I wanted you to focus in this picture is the fasteners there, right here. So here's a picture where the combination that we talked about in the first slide is very present. So you see water, thick metal plates, and also if you take a look at those two screws in the plate above, there's a small gap. That means that the screw has been inserted with an incorrect angle. It's very likely that the screws are being over. Let's say that they're having an unintended stress, like a moment in the head of the screws that will tend them to give an unexpected force. You might have here some wood swelling, then some unintended stressors, and also some corrosion if these conditions are prolonged in time. So bigger construction sites, bigger buildings mean that you have more time in the construction site in an exposed job site. That means also we have more moistures, and that means also we have more stress. I mean, unintended stress. So when we start talking about failures, I would say it's simple. There are some simple factors that can lead to failure. So we know that over-torquing can lead to failure. This is one of the tests that we do when we receive the screws, or we test the batches, we torque them. Well, we put some torsion on them to check how the torsional capacity. We know that if you use a very, in some specific conditions, you could over-torque, you could break a screw with a very potent power tool. In dry conditions. This also happens in steel construction. Of course, you can over-torque a bolt up until it breaks. You can also break a screw or any fastener if you install it with an incorrect inclination. You can just you put it a sufficient bending moment in that head. If the plate is sufficiently thick, you could break it in dry conditions. This happens also in the steel sector and in other sectors, also in concrete. If you insert with the wrong inclination, maybe like a concrete screw. And we finally know, and we know this as well from the automotive sector and from the steel sector, that you can have torque and or wrong inclination. And if you have some internal hydrogen from production process, this is a result of some production processes, especially they are linked to the electrogalvanization, to the electroplating. And this can also lead to failure.
Having a few problems hearing you, Andrés, with your connection. You might like to try. I mean, we missed that last sort of 10 seconds. I think your connection was going a bit funny. I don't know if you want to just repeat what you said in the last 10 seconds.
Okay. Sure. So
You
I think
started
we
talking
stop here, maybe
about
in
the
the
internal
after this one.
hydrogen. It was you'd kind of got to
Perfect. Okay.
internal hydrogen. So only a little bit.
Perfect. Okay. So we know that if we have some hydrogen that comes from the production, and this is completely a factor that is linked to the manufacturing process, especially the electroplating process, in combination with some torque that is not necessarily over torque and some inclination that is not necessarily like too deviated, we could have a failure that is delayed from hours to a few days after the installation, and it's what we call internal hydrogen embrittlement failure. That's a failure mechanism. So this is what can happen in dry conditions. So there are three factors that lead to premature failure. We saw some of them here in the slide before. But let's take a look at what can happen aside from the dry conditions in the whole process or in the whole lifetime of a building. You have it in the x-axis the time from the moment of installation, that's 0, then days, weeks, months, to the design service life, generally 50 to 100 years, and in the y-axis stress. You have that red line also that will give you an idea on the design capacity of the screw. So what can happen at the beginning of the installation is you can have an installation over stress right in the moment of installation that can break the screw. And that will, as I mentioned before, these are dry conditions that generally these can happen to any fastener without, I mean, it's easy to see. Then also in dry conditions, after a few hours to days, you can have internal hydrogen embrittlement. That happens with a very low load capacity, let's say a little low from there. We'll talk about later, but it comes mostly from manufacturing process. Then I'm going again, let me see if I can use the laser. Yes. So here then what you can have maybe in days, once you start having some water, then we're starting being in wet conditions. You can have some installation over stress plus wood swelling. The swelling effect of the timber can also lead to failure when you sum it, add it up to the installation over stress. And finally, from weeks to months after installation, it could be even less than weeks, you could have environmental hydrogen embrittlement, or the same. I mean, a synonym of environmental hydrogen embrittlement is hydrogen-induced stress corrosion cracking, which is the most, let's say, gives more hints of what happens there. We're going to talk about this a lot. This is going to be the focus, because this is a combination of factors, and we're going to try to understand what happens there. And well, I put this yellow line here that gives an idea on what can happen during the building site and in service conditions. Then in service conditions, once the building is closed, well, you can have accidental catastrophic events, fatigue, or corrosion as well. But in this webinar, we're going to focus on building site. That's why we're going to talk mostly about premature failure, because it's we're going to focus on the building side.
Hi, sorry, just quick interruption. A couple of people said that there's just a little grey rectangle, I think on your presentation, bottom right-hand side of the screen. Do you know what I'm referring to?
I
see
think
that, yeah.
That's the, it's the,
Any way we can get rid of that?
Okay, I will
drag it somewhere.
Is it fixed now?
It's still there, but it's very minimal. It's a lot.
Okay.
It's a lot better. It's a lot smaller. If just as a general comment to the audience, if those rectangles are still an issue, then put a note. But if they're there but minimal and it's not disrupting the stream too much, I think we can live with it.
Okay.
Thanks. Sorry.
Otherwise, I can
on.
like close everything. I don't know. Now it's we can work with that.
Yeah, I think so.
Okay. I'm sorry
Okay.
about that. I really don't know what I don't see any rectangle.
Yeah, they're
Okay.
still there, but they're very small now. Anyway, sorry, we should crack
Okay.
on.
Okay. I'll go on. So, well, back to the main factors that lead to premature failure. There's these three. So we have material, stress, and moisture. How is the stress factor? Let's talk about it. It can be over torque, it can be improper installation angle, or accidental loads. But this can, I say, like, they can lead to failure even without any material susceptibility or any presence of moisture. Also, moisture can lead to failure due to corrosion or to wood swelling. Mostly corrosion will induce hydrogen absorption, and this is what we will focus on. And moisture would lead to wood swelling or shrinkage that becomes a stressor, and that's like not like moisture itself that can lead to failure. Finally, the other factor, of course, material alone doesn't entail failure, because otherwise you would have broken screws in a box, and that doesn't happen. But the main factors from the influence failure are the fastener hardness, the coating thickness, and the continuity of the coating, absorb hydrogen during production, and susceptibility to specific agents. For example, stainless steels are very susceptible to chlorine. So in those cases, finding alternative materials can also be a solution. But so these are more or less the factors from the material. Let's focus on the first one, the stressors. So when I mean stressors are unintended stressors, so some stress that the designer cannot or didn't include, of course, in the design. And it can be some accidental load, of course, that can happen. This didn't happen to us. This is just an example I found on internet when looking for accidental loads in wood construction. And well, transport can be an important factor there. But also over torque and proper installation angle. This is a campaign that we did in dry conditions, inserting the screws with max speed in thick metal plates with different angles. For example, here at 80 degrees, 70 degrees. So we know that can break a screw. But also, this also happens in the construction side. This is a construction site that we were present, and you can see the effect of over torquing. These are the ribs on their head that can be seen in the holes of the it's a cylindrical hole with a countersunk head screw, so it was torqued a lot. And then you see there are some signs of over torquing. On proper installation angle, this is also a real case of an inspection we did. And you see also the angle of installation around 13 degrees if it's also somewhat over torqued to improper angle here, that you have then an unexpected stressor on the screw. And you can see it also here, also real case, failure, and also some signs of improper installation angle. You can see also in this case, you see the signs here of moisture. So most likely you have combinations of factors then that can lead to failure. Improper installation angle induces a plastic deformation of the screw, maybe unseen, maybe not that visible to the naked eye, but can lead to some plastic deformations and also break the continuity of the coating, leading to potential corrosion in those parts, in those points. So let's talk about the moisture factor. So we have the wood swelling and shrinkage effect. Let's start about it, talking about it, because it's more related to stress. And well, we actually have done some tests on that. You can see this is a very how to say it, it puts the problem or the consequences of swelling right up front. So, and it gives an answer also on why this happens with steel thick metal plates compared to thin metal plates. So in a thin metal plate, you see how so these are we're completely dry samples that we put in water, and you see the deformation after some days. And thin metal plate can have deformations with along that will follow the deformations of the wood element, thus redistributing the forces. And of course, the part of the screw is binded pretty much on the screw. When there's a thick metal plate, you will have probably no deformation around the screw or the metal plate. Thus, the energy from the deformation or the forces will be transmitted to the screw. And that's why this is a worst case scenario. We also tried with a damping element. You see here, this is an acoustic profile, a soundproofing profile, and it has a lot of a positive effect. We're not going to talk about this, but this is just to show the effect of swelling and shrinkage. And this is very limited also to one screw, one thick metal plate that is pretty much the size of the wood sample also. So we think that this is not even the worst case scenario for wood swelling. We are not considering also the binding effect. This can make it potentially worse, and this has to be researched. But to explain more or less what can happen, and that makes it a bit more problematic, is that in a case like this, or in a job site that comes into the connection, then we have some forces from the deformation while the tip of the screw is in a drier place. Which has higher mechanical performance of the wood. Thus, the screw has higher withdrawal capacity compared to the rest. And then you have a differential relative deformation. So the screw here is very stiff. Then it finds another stiff element as the plate, and the wood will deformate close to the head, pushing the screw in the upper direction. We did some tests with the University of Alberta. You see, these are more or less the samples that I showed before. We put them in some cut bucket where we then pour some water, and with load cells, we measure the effect of swelling, the upper force, the force going up. We start with control torque, sometimes with over torquing and sometimes without over torquing, and we measure the effect of the swelling. So what you see here, these are the first seconds from installation. Right when we install it, we give it, this is recommended installation torque, which is more or less 18 Newton meters for this screw. So with 18 Newton meters, we give the screw more or less 7 kilonewtons. Yeah, so we start with that stress. We have an immediate relaxation of more or less 1 kilonewton, and then we hit more or less a plateau right here. Okay, so we in the around 7 kilonewtons if we take a look at the black curve, and then at 24 hours right here we add water to the sample. So what you see here, after 1 day we put some water. So this seems to be an horizontal curve, but actually it will tend to decrease a lot. So do we have an initial relaxation, and this is very, very relevant, of more than 1 kilonewton for the screw. And when we pour some water to it, you see that there is a big bump. If we take a look at the red curve, you see that we have an increase it will go from 5, let's say, from 5 to 11. So it's a lot of force that's coming from the swelling effect. Here the increase is a lot, and it's hard to say how this is if these are two effects that can sum each other in the construction site in a real case. But if we take a look at it as a worst case scenario, then we think it is very relevant to be considered and to be studied a bit further. When we then put the an overtorque sample of 30 Newton meters. Then instead of the initial 6 we had, we are at 10 kilonewtons. And we hit a plateau more or less at 10.9. So we start with a lot of more of pre-stress. And we have a smaller reduction, so a bigger initial reduction, but then a smaller plateau. And we hit 12. So that means that the swelling, that the higher the over torque, the less is the swelling effect. Nonetheless, we have a final result of the over stress that is even higher. So we are still at 12 kilonewtons. We expected these experiments, or at least this phase, these samples, to break, but actually we found out that these two factors, over torquing and swelling, at least in these cases, is very important. In this case, they do not sum. So there's not like the more over torque you have, the more is the swelling effect. But because you have more or less of a sponge effect. If you have a sponge in your hand and you add some water, the sponge will not increase its volume because it cannot absorb. It's not allowed to absorb. So our conclusion here is that the effect of over torque, so the force given by over torque plus the force given by swelling, can get to roughly 60 to 65% of the tensile capacity of the screw, which is a lot. It's a lot for a pre-stress. We didn't got to a failure, and we are really we don't know if ever like only over torque and only swelling will lead to failure. Nonetheless, it is a very significant pre-stressor in steel, especially in thick plates to timber connection, so around 65%. That would mean that well, this is a bit of an exaggeration, so take it for what it is. But right now, as designers, we consider the force during the design phase needs to be below the force or the tensile capacity of the screw. So this is very, very roughly. So there are two factors that we're definitely not considering, which is the over torque force and the swelling force. All three of them should be lower than the tensile capacity for the design to achieve the design life. But they need to be handled differently. So of course the over torque could be mitigated with correct installation, and the effect of swelling in maybe some considerations in the design phase. I really have no precise way of establishing how to consider the effect of swelling, but this is an input for future standards to consider the different effect. I know the Canadian standards have something more specific for swelling, but not in the Eurocode 5 is there some specific consideration. And finally, a motion control plan is fundamental to reduce this factor. But it's not only about force, it's not only about understanding the stress. We are going to talk about the effect of corrosion. And I like this picture a lot because it shows, it seems that it's just a corroded nail, but this is a nail that is corroded in two different ways. So we have definitely some corrosion here. So if we checked the components of the elements here compared to the components with the element here, we would find different components. Here we would find maybe salts, maybe chlorides, maybe chlorine, while here inside we would find tannins. We will find subproducts of wood acid. So these are two different effects, two different phenomena that are attacking the screw, and they need to be handled differently. We will focus more on the part of the hydrogen absorption and why is this relevant. So, well, as I said before, there are two different factors. We have atmospheric corrosion classes and wood corrosion classes. Now in the new Eurocode, they are going to be introduced. And we need to consider them. So of course, the atmospheric corrosivity classes, they will affect the exposed part of the screw, while the wood corrosivity classes would affect the part that's inside. And the surface class will give us an idea of how much of that effect will be. we need to focus in this case, if we're talking about premature failure, since we are talking about months and not the design life of the building, not that much on the atmospheric classes, but a lot on the wood corrosivity classes, which are linked to the service classes as well. So when we talk about wood corrosivity classes, this is generally overlooked. We generally know that, I don't know, treated wood is corrosive, that some hardwoods are corrosive, but less is, we have not that much information, some precise information about it. And this is what it looks like. So generally, in a case where atmospheric corrosion is not a problem, but wood corrosion is, because we have maybe an exposed environment, a humid environment, we will have like some, well, the exposed parts are okay, but then we have some signs here. And as you can see in this example, the corroded part is what's inside of the screw, and even the plate that's in contact with the wood, in this case, if the wood is corrosive. And this is what it looks like. This is the same example, the same connection that I showed before with the incorrect angle. So just to tell you, to give an idea, because these things generally mixed. So we generally have incorrect angle. We generally have also some moisture that leads then to corrosions. And in this case, when you took out the screw, you see after some months inside, the environment was definitely corrosive. The environment inside of the timber. So we know there had to be a certain level of humidity to then produce this type of corrosion. This amount of corrosion of the screw. So we have white corrosion, black corrosion, and even some dots of red corrosion. So they have an advanced corrosion process. And the point with this is that we need to select the proper screws, the proper coating, corrosion protection for, or choose as well the proper corrosion protection in how to say it, considering the risk that we want to take or that we don't want to take. So there are different stainless steels that go from martensitic 410 to HCR. Are also many many coating types for the carbon steel that goes from zinc plated to different proprietary coatings like organic coatings, C4, C5, Evo coatings like Rothoblaas does. But depending on the corrosion protection that your project needs, and the uncertainties that you might have also in the job site, you can choose a different corrosion protection for lower the risk in the construction site. So back to the factors. We saw each other on its, let's say, individually, but now we're going to talk about how they combine to produce premature failure. So if we take moisture out of the picture, we talked about at the beginning, if we have some stressors, unintended stressors like insulation torque, improper angle, and accidental loads combined with a material which is particularly hard and with some absorbed hydrogen during production, then we can have internal hydrogen embrittlement failure. How we recognize it generally happens from hours to days after installation. This is very critical, so because it happens in dry conditions mostly. So we don't have the effect of moisture, and this happens very early. And most important, this is responsibility of the manufacturer. So most cases this happens. If this happens, this is, let's say in this case, if we are providing the screws, and if it's proven internal hydrogen embrittlement, this is on us. Why does that happen? So we have some, these three, well, there are many, but many processes can induce some hydrogen, but none of them are as relevant as these three. And even from these three processes, from heat treatment to galvanizing to pickling, the most important one is definitely pickling process, which is one of the processes during electroplating where the fasteners are put into some acid baths that then will then induce the absorption of hydrogen. But I really don't want to get too much into detail with this part. because this is really like this is manufacturer's responsibility, what we do, and this is mostly state of the art and the industry, but also we definitely do in our production processes, is incorporating inhibitors in the pickling baths, a lot of in-process control and testing. For some screws, we have de-embrittlement baking. Also, internal hydrogen embrittlement testing is fundamental as per ISO 15330, and then storing the screws in dry and controlled environments to maintain their integrity. And that's it for internal. Let's go to the elephant on the room. Let me check the time. Okay. Environmental hydrogen embrittlement, I think I will take just maximum 10 minutes. What we need for internal hydrogen embrittlement to happen, the only factor that is not that relevant here is the absorbed hydrogen reproduction, because we will have hydrogen, but that hydrogen that doesn't come from the internal, but comes from the environment. And this happens from days to weeks after installation. This is more or less of a chemical explanation of what happens. I won't go too much into details, but we need a force and we need some corrosion happening. This will, as a subproduct of the corrosion, we create some hydrogen that would then get into the first and most external layer, and it will be absorbed to the inside of the section, let's say, of the fastener, and then in the presence of a discontinuity of the coating, it will I would say it will induce crack formation and crack propagation, and then with the sum, let's say, of different cracks, it will lead to failure. Another way to explain it comes from its second name, which is hydrogen-induced stress corrosion cracking. So we need stress, we need corrosion. These two factors will induce cracking, and they come from hydrogen. So what happens is that the corrosion produces hydrogen, corrosion of the zinc mostly, and it will create and then in the presence of an interruption of the coating, that it might come from a corrosive environment of wet timber for a long time, which will produce some surface corrosion, but it will take some time. Then it will then lead to failure. Another way of this interruption of coating happening is that we have some over torque or some improper installation angle that will damage the coating, and this will happen quicker because the interruption of the coating from surface corrosion happens very slow. But if it comes from damage of the coating, then that interruption can then lead to corrosion and then hydrogen, and then we will have the phenomena that we saw before. So if we take a look at this, the factors that would increase the risk of hydrogen embrittlement, we have mostly these three: the hardness of the fastener, the tension that they are subject to, and the presence of hydrogen. So this is in the case of environmental, it's linked to corrosion. So the more moisture there is, the more corrosion there is, and thus this element is increased. How do we tackle it? So the fastener hardness is tackled with control manufacturing process. This is a responsibility of the manufacturer, and it will reduce material susceptibility. The sustained tension, of course, mitigating unintended stressors. We're talking about avoiding mostly installation over stress. And also, the hydrogen factor, we will mitigate it by protecting connections from moisture. We will then, if we protect them, we will avoid corrosion, and then the hydrogen that's generated from corrosion, and the swelling effect, which is more of an unintended stressor. What do we propose as tool for to evaluate the criticality of the connections? And this is well, a risk evaluation matrix is of course a term or a concept that comes from especially from people that work with the insurance, or how to assess the risk. But if we're going to make a proposal focused on the connections themselves. So we will give a risk value, and then adding up the risk value, we will have a final value that will let us know where to focus our efforts. So if we talk about the type of connection, we have wood to wood in softwood, that would be a low factor case scenario for us. Also, but if you have like a wood to wood hybrid, maybe you have LVL with CLT. In that case, we will have some relative stiffness difference. Or thin metal plates, that would be a mid-risk case scenario. Finally, high risk would be steel to wood, especially with thick steel plates. That would be our high risk. And also the moisture content of the project, of the connection, let's say in project, we service class 1, 2, or 3, depending on that, it will increase the value. We think these two risk value factors come from the design plan, so these are mostly assessed by the designer. Another two factors would be the presence of prolonged unintended overtension. This is hard to control because this comes mostly from the executioner. And so the way of tackling is, well, from a good execution plan that would prescribe the manufacturer's installation guidelines. But also at the end, it would depend on the experience of the installers. So we can have low or no overtension if we are doing everything as intended, moderate overtension, and high overtension depending mostly on the installers if we have incorrect installation due to excess torque and/or inclination. And finally, exposure to moisture during construction. This is critical. We might have dry conditions, let's say we call it fully protected connection, partially dry conditions, or wet conditions if the connection is completely wet. And also a part of it will be the fastener specifications. I mentioned it before. We can choose a fastener that it's more or less prone to, that is more or less, let's say, susceptible to corrosion. So if we have no coating at all, that would be a high case scenario. It would be unreal, but it would be some connections are, I mean, even the Eurocode would allow you to have no coating in some cases, but also you can choose having a proprietary coating of stainless steel in some cases, and it would lower the risk factor if you know that you're going to be exposed. So I'm not saying that you need to work every time in low cases. Of course, not every time you can work only with wood-to-wood connections, but then some of the factors you can choose to move from one place to the other. At the end, if the sum of all the factors that you have in a connection falls into one of these three categories, you will have low, medium risk, and you can distinguish from the connections in your plan where to focus your efforts. So, for example, if you have a wood-to-wood connection in service class 1, but you have no idea of the installers, they might be unexperienced. You have wet conditions, and you have a standard coating with standard hardness. You will have, in this case, 1, 2, 5, 8, 10, 12 factors. So you will fall into the medium risk. If you want to be completely, I mean, I would just suggest to things that you can change to go to low scenario. You can maybe hire or prescribe a very detailed installation execution plan and lower the presence of overtension, and also protect the connections, then to go from wet to dry conditions that would put you in the low risk. So this way, we think we can give a hand on how to lower the risk in some connections. But of course, this is a concept draft, and we don't intend you to use this one, but to create your own so that you can know the type of risk and manage the type of risk that you have in your connections. Finally, I gave some hints before on what we think are the most important players, stakeholders in each type of premature failure case. We think when we're talking about installation over stress, this is mostly the installer. It depends, of course, on the execution plan, on how clear was the execution plan, but at the end, the responsibility or the the main factor would fall into the installer. Then we have internal hydrogen embrittlement. This is completely manufactured here. So again, this here, falls. I mean, I showed what we have to do in order for this not happening. Then we have installation of truss and wood swelling. I think in this case, we have some installer responsibility and some designer responsibility. We have prescribed correct protection for the connections, correct protection for the general job site, and this would mitigate the effect of swelling. And finally, environmental hydrogen embrittlement has to do with these three factors, which are material, moisture, and unintended stressors that come from installation. So this is a shared responsibility from all three of us. And that's it from my side. Thanks.
Thank you very much. You've covered a lot. Thanks for speaking non-stop for so long. That was much appreciated. Quite a few questions have come up. They sort of echo a few things that I was wondering about too. I'm going to try and sort of summarize them in sort of clumps. We had a few questions sort of asking about time periods, as in, you know, once screws have been installed, assuming they've been installed correctly, if they were to be suffering from hydrogen embrittlement that was, say, part of the process from the manufacturers, can we say, you know, how quickly you would notice a problem? Are you talking days, weeks, months? Or if there is a problem in the manufacturing process, can it just hide for years, or would it be something you would encounter very quickly?
Yeah, that's one of the reasons I wanted to. This line is very important because this is a problem that is hydrogen embrittlement in general, whether it is internal or environmental. This is a problem of the construction site. So internal hydrogen embrittlement doesn't require an effect of moisture, so it will happen literally hours. Can happen from hours after the installation to days after installation, no more than that. Really, it takes no much stress, and it generates the installation stress enough for internal hydrogen embrittlement to activate. Then environmental hydrogen embrittlement will depend on how on the exposure to moisture, let's say to an aggressive environment. If there is an aggressive environment, then environmental hydrogen embrittlement can happen. I'm talking here about, let's say, indoor intended connections. If you have a exposed connection, then this situation can extend into the service conditions. But I won't talking mostly about, let's say, more of an indoor case. So yeah, I think I answered your question.
Yeah. Thank you. You also, I noticed you mentioned on one of the slides there was an ISO 15330, and a couple of questions had asked what sort of guarantees or promises manufacturers can give. I mean, you showed some of the Rothoblaas things, you know, during the inhibitors during pickling and various other things. But was that the ISO that you mentioned? Does that kind of guarantee that that measures have been taken by the manufacturer against hydrogen embrittlement during the process?
That's its objective. So ISO 1530 is a test method that would put a screw, a fastener after production in tension at more or less 80% of its ultimate capacity for 48 hours. So we test some screws every batch for every production batch of the screws, and the idea is that, of course, it's a statistical, it's a probabilistic, let's say, test, because of course we do not test all the screws because we need to. It's a destructive test, but we test a bunch of them, and we put them for 48 hours. And if after 48 hours we do not have a single failure, if only one screw fails, then we need to take some action into that batch. But if we have not signs of failures, then we will waive the batch, and then we put it on sale. And it should give an idea on if the proper measurements were taken into the production process. Yes.
And we had a couple of questions when you showed that slide showing the corrosivity class diagram, which I think a lot of people were very interested in. For me, that was really instructive because you could sort of see the sort of types of wood, types of coating. I'm sorry, I may be mixing up a couple of slides here, but it was instructive for me, and I think quite a few people watching to sort of to get a measure of I suppose that the types of fixing that you might be specifying. Do Rothoblaas, for instance, if you were to come to Rothoblaas with a specific project and talk about a this very specific environment that this project was taking part in, would you be able to give kind of specific guidance on, you know, whether you should go to, for instance, you know, a martensitic stainless steel I can see there, and all the other various coatings? In terms of risk management, if you know what kind of wood you're going to use, the kind of coating that wood has, the sort of the weather environment it's likely to encounter, how can you then make a very informed decision as to what type of screw and what type of coating you should be using? So hopefully that question makes sense.
I think yeah, it does. It does. I think this answers to the fact that we don't have specific guidelines for the job site. I think. I mean, guidelines are not complete, I would say, for designed life, but they are better. Eurocode 3 Part 4 gives a lot of guidance on how to choose the proper stainless steel. But when it comes to the Eurocode 5 or guidelines for let's say for carbon steel screws, coated screws, yes, but not about the job site life. So in this case, it needs to be a risk-based approach. If we know, because for the Eurocode 5, it doesn't matter if the job site will stand 1 month or if it will be a 2 years construction site. That means that if we're talking about zinc-plated screws, which are completely produced like with a correct coating, with a correct thickness, they will be sustaining a level of aggressiveness that they won't be designed for if they are exposed 1 year to fully exposed conditions. 1 year of fully exposed conditions is literally is really a lot for a zinc-plated screw. So this is a risk that, of course, we can assess, that we can give guidance for the selection, and that will very likely lead you to choose another type of coating, maybe an organic coating that was engineered for sustaining a service class 3 condition, wood corrosivity class 3, or if we are closer to the sea, maybe a C4 Evo, so able to sustain an atmospheric class C4 and a timber class C4, a wood corrosivity class C4. So this is the work of a lot of years of knowing which type of coating works better or not, but also it comes to assessing a risk scenario, the correct risk scenario for the conditions, in this case for the job site.
Great. Yeah, I mean, a couple of people asked actually if that slide, that is available anywhere. You know, are there any publications that sort of where people?
Yeah. Yeah, there's a Rothoblaas smart book for timber screws. And we dedicate a complete chapter on corrosion, on the effect of corrosion, explaining atmospheric corrosivity classes, wood corrosivity classes. And even, I didn't talk about it here, but another factor is galvanic coupling, which is a relevant factor also in the job site period. I just cannot cover everything in 1 hour, but that all we talk also about that there, and what we need to avoid also galvanic coupling. How do we handle if we cannot avoid galvanic coupling because we know we have a facade? The facade needs to be in stainless steel.
We've lost you, Andrés. Do you want to try just turning off your video for a second? You've just suddenly completely frozen. I take it that's not just me, and that other people have also perhaps lost Andrés. Andrés was actually joining us from Taiwan, so his connection has been not perfect. Yes. I think we might have to draw things to a close as we have reached 2 p.m. anyway. So I think we were very lucky and privileged to have Andrés sharing his wisdom for a good solid hour. I will endeavour to round up all the many questions in the Q&A box and forward them to Andrés, because I had a few as well. So apologies that there was a rather abrupt end to this webinar, but I'm sure you'll agree there was a whole slew of very, very valuable info there. And as mentioned, I will pass on any further questions to...
Sorry, here I am. Sorry, I think I lost the connection before. Here I am. Sorry.
Okay, you're back again. And I was actually just about to wrap things up because I wasn't sure if you would be back. I suppose if you do have one more minute, I was going to ask about inclination, because there were a few questions about that. In terms of, do you have guidelines, I suppose, on inclination and angles for the products that you sell? You mentioned I think you had a slide showing various screws, and you did mention something about them having information on angles on them, if I understood correctly.
Yes, so I mentioned there, I will show my screen again. Sorry, real quick. And so, yes, I showed, I think it's this slide and this one here. So these are the effects of different inclination on inclination angles on the screws. So of course these are exaggerating. Inserting a screw 50 degrees on a perpendicular hole is completely out of question, out of sense. But yeah, we do actually what we think is the first standard for execution, which is the Eurocode 5 Part 3, has some recommendations specifically for fasteners and for the installation of fasteners in steel to or metal to wood connectors. They recommend more or less 5 degrees maximum. We all find that the safest way, or let's say that's the only deviation that use permanent or a permanent effect. There is a plastic deformation, because 5 degrees is pretty much within the elastic range of the screws. But mostly because the elastic range is bigger than 5 degrees, it will not entail discontinuity on the coating, which is a very determining factor in that when we're talking about corrosion and then about hydrogen embrittlement.
Thank you. We have gone over time a bit, but this may be an impossible question to summarize, but somebody has just asked the sort of overall question: how do we go about best practice quality control and ultimately be sure that the screws won't break in the long term? Now, obviously, you showed us the risk control diagram. So you've pointed to the importance of a moisture control plan and other things. But if you had to condense it all down and answer that question, what is the best way to ensure quality control that screws won't break in the long term? Is there a summary you could leave us with?
Well, yeah, if I had to choose for a very quick answer, a direct answer, the long-term effect that is most important is the moisture management, definitely by far. Because the effect of over torque, for example, we saw that you have some relaxation on time. So you might have some damage that you induce to the screw, but if there's no corrosion on time, if there's no presence of hydrogen, it might not necessarily lead to a weakening of the fastener. So it might be an elastic deformation or something that the screw was able to sustain because of its robustness. Generally, of course, they have a lot of safety factors there that are inside of the screw, so it can be that they are not that it's not that high. Same for the effect. Generally the unintended stressors, and also the about the manufacturing processes. It has been demonstrated, and this is a thing that needs to be researched upon, but hydrogen from manufacturing tends to diffuse in atmosphere, in ambient temperature, let's say. Stored fasteners are liberating hydrogen right after they are finished in the manufacturing process. So generally, and that's the case, for example, from Rothoblaas screws, from production to selling, generally months pass from in stored conditions, and this is becoming state of the art of knowledge about hydrogen embrittlement. It's the most likely case is that in that time hydrogen has been diffused into the environment, so there's no more internal hydrogen. So if we take this into considerations, then the moisture problem remains, and it's definitely the most critical, because even with very low hardness of the screw, and even in with no hydrogen, uh, if we have moisture, then we can have corrosion, and this corrosion can then lead to corrosion itself, which is harmful on its own, but also to stress corrosion cracking, because these screws are of course loaded, and if then with some other factors like unintended stressors that are overloading the screws, then they can leave it more prone to failure. But at some point, if you take a look at this slide, the effect of corrosion on its own can lead to failure, and the effect of corrosion with some induced overstressors can lead to failure, and are the ones that are more in the long term of the effects here. And that's pretty much the objective of these slides, to have an idea of when this phenomena happen, so that you have an idea on recognizing, okay, what could have gone wrong, and who is to be taken to ask the accountability for the failure.
Great. Thank you very much. That's been a really informative and insightful hour. Thanks so much. So I think we'll end it there. On the topic of moisture management, there are several documents you can find on the Timber Development UK website. I think I showed one right at the start, moisture management during construction, and we will be publishing a template moisture control plan in 2026. So watch out for that. But yeah, thanks again to Andrés, and goodbye to everybody. Have a great afternoon. Thank you.
Thanks to you.